In this presentation, we're going to look at, this is a telescoping series example. So what we're going to do is find the sum of the following telescoping series. It's a sum to infinity. Okay, so watch out for that. So it's going to sum to infinity essentially. So what we're going to do here is we're going to restructure this expression here. This is the main component here. 4 over 2n minus 1 times 2n plus 1. And what we're going to do is restructure it. We're going to split it up into two separate fractions. So we have 4 divided by 2n minus 1 times 2n plus 1. We're going to split it up into two fractions. We have a over 2n minus 1 and b over 2n plus 1. Okay. Now this bit I'm going to sort of go through very quickly. It's essentially what we have to do is cross multiply and let the numerators equal to each other. So if we cross multiply and let the numerators equal to each other, we will get this expression here. 4 equals a times 2n plus 1 plus b times 2n minus 1. Okay. Now, let's simplify that. That is equal to 2an plus a plus 2nb minus b. Okay, and let's restructure that as 2a n plus 2n, or 2bn, sorry, 2bn, doesn't matter really, plus a minus b. Okay. Now what we have here on the other side is 4, but what we could do here is briefly write that as 0n plus 4 just to provide a bit of clarity. So what I'm going to do here is just like rewrite the right hand side one more time. So we have 2a plus 2b times n plus a minus b. Okay, and as a result of that, we could say that 0 equals 2a plus 2b and 4 equals a minus b. These are just the sort of lettings. Let's just sort of show you what I mean by that. This part here, 0n, corresponds to this part here, 2a plus 2b times n. And this part here, 4, corresponds to a minus b. So we're just letting the two components correspond to each other. So 0 equals 2a plus b. What we can also say from that is 0 equals a plus b, multiply both sides by 2, or that's a equals minus b. Okay, so let's use that and substitute it into there. And what we could say here is that 4 equals minus b, or other words, minus 2b. Therefore, b is equal to minus 2. A necessarily is equal to plus 2 because it's minus b. So it's minus minus 2. So we have a and b are 2 and minus 2. So let's just set up our expression here again. So we had sigma to infinity of n minus 1, n equals 1 of 4 over 2n minus 1 times 2n plus 1. That can be written as a was 2, so 2n minus 1, minus 2 over 2n plus 1. Okay, sum that to infinity, or sum that to infinity also. Okay, so what we're going to do now is evaluate it for each expression just to sort of finish this off. So u of 1, that is equal to 2 over 1 minus 2 over 3. N here is 1, 2n minus 1 gives us 1. 2 times 1 minus 1 is 2 minus 1, and plus 3. The next one is u2, and that is 2 over 3. N is 2, so 2n minus 1 is 4 minus 1. 2n plus 1 is 5, so it's 2 over 5. And so on. u3 equals 2 over 5 minus 2 over 7, and so on. You get the idea now. But essentially what we're saying here is that the sum equals u1 plus u2 plus u3 and so on. So what we're so let's all add up all of these here, and sum them all up. So let's just sort of restructure this now. And so when we're adding u1 and u2, the minus 2/3 and plus 2/3 cancel out. Okay, so we're 2 and minus 2 over 5. We add u3 onto that, minus 2 over 5 and plus 2 over 5 cancel out. Likewise, minus 2 over 7 will cancel out with the next thing. Okay, and so on. So what we are actually left with is 2 or is essentially 2. The answer just works out to be 2. All the components will cancel out, so the answer will just end up being 2. So that's a telescoping series worked example. The idea of telescoping series, again, just to be clear about this, is that you can restructure, there we go, you can restructure your expression as two sort of separate fractions, two simple fractions, and when you add them all up together, they cancel out. That's the idea of telescoping series. Okay. Oh, by the way, the numerators on this numerator and this numerator have to equal each other for this to work as well. They have to be equal to each other. Okay.